So today we are going to cover section 10.1, the first section of chapter 10. We're only going to cover two sections of chapter 10. So today, section 10.1, and next Tuesday, section 10.2. Follow that, we're going to have the review for the last test. So before the review, I will email you to recruit questions and formulas for the first test. All right, so that's the plan. If you want to know the plan, the details of the schedule, the rest of the semester, look at our syllabus. We follow the syllabus, the last part, tentative schedule, very well, actually. All right, so 10.1 is about correlation. What is correlation? Correlation describes a relationship between two variables. The formal definition of a correlation is right here. A correlation exists between two variables when the values of one variable are somehow associated with the values of the other. And correlation includes linear correlation and nonlinear correlation. And our class, this chapter, focuses on linear correlation. And what is a linear correlation? Linear correlation is the correlation relationship that follows a straight line pattern. As it describes here, a linear correlation exists between two variables when there is a correlation and the plot points of paired data result in a pattern that can be approximated by a straight line. So the correlation, the relationship has a linear pattern. To determine if there is a linear correlation exists between two given variables, the first thing we normally do is to visually examine the scatter plot of the two variables. So that's the first step, visual examination. Yeah, just look at a graph. What kind of graph? Scatter plot. Scatter plot. Let me explain what is a scatter plot. Scatter plot is a two-dimensional graph. So it describes the relationship, is able to describe the relationship between two variables. Normally, variable x is on the horizontal scale, the values of variable x, and the variable y will have the values of variable y on the vertical scale. And for each value of x, for example, x1, there should be a corresponding value of y for variable y. Then we would have a pair. And this ordered number pair corresponds to a point in a rectangular coordinate system. Yeah, suppose we have n values from both from each variables of x and y, then we would have n number pairs, n order number pairs, and they correspond to n points. Yeah, we understand this, right? Because if you have learned algebra foundation, you know that we define points in a rectangular coordinate system as a ordered number pair. Yeah, there is a one-to-one correspondence between ordered number pair and the point in the rectangular coordinate system. So for those n ordered number pairs, we would have n points in the rectangular coordinate system. And if those points give you a linear pattern, yeah, either goes up or goes down, then we would go ahead to do further investigation. Yeah, we will go further to actually calculate or the value of the correlation coefficient. Yeah, the value of correlation coefficient measures the strength of the linear correlation. If the scatter plot does not show up, does not display a linear pattern like this one or this one, as you can see, the one on the bottom left, you can see there's no pattern, right? Yeah, if obviously from your sample, the two variables doesn't have really obviously there isn't a linear pattern between the two variables based on the sample, we normally do not go ahead to calculate R. Yeah, but you can see our example here does have the value of R. R equals 0.074 is pretty close to 0. When the correlation coefficient very close to 0, that means the linear correlation does not exist between the two variables. Well, there's a possibility that there is a correlation relationship between two variables. It's just the pattern is not linear pattern. Like the graph on the right bottom, as you can see, there is a pattern, right? But the pattern is not linear. It's actually a parabola. Yeah, that's a quadratic pattern. It's a quadratic correlation relationship. Yeah. So the corresponding linear correlation coefficient R is also very close to 0. Yeah, when this happens, the pattern exists, but the pattern is not linear, and we do not investigate it further either. Yeah, only when the scatter plot shows the pattern, then we go ahead to calculate the value of R. The graph on the upper left, you can see a linear pattern goes up, right? Yeah, this graph to the right next to it, we can see a linear correlation goes down. So the one on the left is a positive correlation pattern. The one on the right is a negative correlation pattern. It's pretty intuitive, right? Yeah, it goes up, slope is positive, so positive correlation. Goes down, slope is negative, so negative correlation. Yeah, again, R here is called the linear correlation coefficient. It measures the strength of the linear correlation. As you can see, the one on the left, the R is positive, the one on the right, R is negative. Yeah. So when the correlation coefficient is positive, it indicates a positive correlation. When the linear correlation coefficient is negative, it represents or indicates a negative correlation relationship. The pattern goes down. And also, as you can see, compare with the first graph, the second graph, the points are more closely scattered around a straight line, right? Yeah, compare with this one, the kind of the points are a little bit further away from the straight line. So that's the reason the absolute value of R on the right is bigger than the absolute value of R on the left. So when the absolute value of R very, very close to 1, that means the strength of the linear correlation is very, very strong. Yeah, the closer to 1, the strength, the bigger of the strength of the linear correlation. Yeah, so those are just something very basic about linear correlation coefficient. Yeah, and now I can show you the formal definition of linear correlation coefficient R. Yeah, we need to remember the notation is R. We use the lowercase letter R to represent the linear correlation coefficient. Okay, linear, keyword linear correlation coefficient. So this value only measures the strength of the linear correlation, not any other types of correlation. Yeah, let's look at the definition here. The linear correlation coefficient, R, measures the strength of the linear correlation between the paired quantitative X values and Y values in a sample. The linear correlation coefficient R is computed by using a formula. Do not worry about the formula. I know how big this formula is, but don't worry about it. We have a tech knowledge. Yeah, we're going to use the formula. You can use the formula to calculate R, but we don't really have to, all right? Another name for R is Pearson product moment correlation coefficient, in honor of the developer of the concept, Karl Pearson. Okay, so it's just some extra information here. About R, it has the following properties. As you can see from the formula, R has no unit. R has no unit. So it doesn't matter what's the unit of X, doesn't matter what's the unit of Y. R is a value without unit. Number two, in the formula, as you can see, X and Y are symmetric. So if we switch the order of X and Y, it does not change the value of R. It does not change the value of R. That's a second property. Okay, so actually I just described number 2 and number 3. And number 1, the value of R is between -1 and +1. This one is very important actually. R is always bigger than or equal to -1, less than or equal to +1. Yeah, when R, the value of R very close to 0, it indicates there isn't a linear correlation between the two variables. When the value of R very close to +1, it indicates a strong positive correlation relationship between the two variables. When the value of R very close to -1, it indicates a strong negative correlation relationship between the two variables. So this is a very important property, the first one. Number 4, R measures the strength of a linear relationship. It is not designed to measure the strength of a relationship that is not linear. Number 5, R is very sensitive to outliers. It does very sensitive to outliers, in the sense that a single outlier could dramatically change the value. Yeah, later we're gonna have similar related question to explain this property of R. All right, so normally that's the process to determine if a linear correlation relationship exists between two variables. Yeah, we do visual examination, construct the scatter plot. Yeah, I would show you how do we construct the scatter plot for two variables if the values of the two variables are given by using TI-84 calculator. And then look at the scatter plot, we would know if it's necessary to go on and find the value of R. Yeah. Again, if it's something like this or this, then we don't have to really continue, right? Yeah. So to find the value of R, we would have the technology available. We don't really have to use the formula here. Yeah, again, R is between -1 and +1. When the absolute value of R close to 1, it indicates a strong linear correlation relationship. When the absolute value of R close to 0, it indicates a very weak or no linear correlation between the two variables. Also, we can use the hypothesis test. Yeah, we have learned 2 chapters, chapter 8, chapter 9, both of them are about hypothesis tests. And this chapter, we also could use the process of hypothesis tests to test if there is a correlation between two variables. And what we need to know about this part is for the hypothesis test of the linear correlation, the null is always be rho equals 0. The null is always rho equals 0. And you might wonder, what is rho? Rho here is just represent the R actually, okay? Yeah, rho here actually represent the R. Yeah, rho represents the linear correlation coefficient, yeah, of the population. So technically, rho is a parameter, R is a statistic. Yeah, the relationship between rho and R is like the relationship between mu and x bar, or the relationship between sigma and s sub x, small x. Yeah, so rho is the linear correlation between the two populations. Okay, because the test is always about the population, and R, the value of R is from a sample, so R is a statistic. If you really want to know the notation, that's the explanation. So our null is always rho equals 0. We always assume, yeah, for the hypothesis test of linear correlation, we always assume there's no correlation. If R equals 0, there's no correlation, right? Yeah, if the linear correlation coefficient is 0, there's no correlation. And the alternative is always not equal to. Okay, always not equal to. So it's a two-tailed test. It's gonna be a two-tailed test. Two-tailed, what type of test? It's gonna be a two-tailed t-test. T-test with the freedom of degree of freedom equals n minus 2. Okay, with n minus 2 as the degrees of freedom. And here we have the test statistic. The numerator is R. How do we get R? Right here. And the denominator, yeah, those are the value of R depends on the values of X and Y, right? The sample. And the denominator is a square root. Square root, the radicand of the square root has a quotient, is a quotient. Numerator is 1 minus R squared, denominator is n minus 2. Again, we don't really need to know the formula since we are going to have the TI-84 calculator to help us to find the value of the t-test statistic. T-test statistic. But what we need to know is the degree of freedom though. Yeah, that's something we need to know, okay? N minus 2 is the degree of freedom. Same with the hypothesis test we have been learning in chapter 8 and chapter 9. We have two methods. One method is the p-value method. The other method is the critical value method. P-value method, you can use the calculator quickly to find the p-value and then compare the p-value with alpha, the significance level. Same with earlier. If the p-value is low, no must go. Means we're going to reject the no. Reject no, which is we're going to reject there's no correlation. So we support there is a correlation. If the p-value is high, no must fly, remember? Yeah, then we fail to reject no. Then we do not support there is a correlation between the two variables, linear correlation. Yeah, by the way, no correlation or correlation, of course, here refer to linear correlation. Okay, yeah, so the whole time we only talk about linear correlation, not any other types of correlation. P-value method is very straightforward, similar with earlier, I mean chapter 8 and chapter 9, but critical value method is a little bit different. Okay, yeah, critical value method is to compare R, not a T, not a statistic. Yeah, we compare R and the critical value. Since it's a two-tailed test, so we have two critical values. Yeah, one positive, one negative. Yeah, they are going to be opposites of each other. So this is a 0, right? Yeah, so this is the negative critical value. This is the positive critical value. And this would be the critical region in the left tail. This would be the critical region on the right tail, in the right tail. Yeah, they are symmetric. And you are going to look at where does R fall. If R fell in the blank region, then we fail to reject no. If R fall the shaded region, then we're gonna reject no because the rare event occurs. And how do we find the critical value? We use the table, okay? Yeah, we're gonna use the table. The table normally is given from the question. I could also include that in the formula sheet. Yeah, so this is the linear correlation critical value table. Yeah, we're going to use that to find the critical value when we use the critical value method to test the claim regarding the linear correlation coefficient. All right, yeah. So those are just the theory. Of course, without actually using it, you probably don't know what I'm talking about right now. Yeah, so we are going to use it right now, okay? So I have the questions here. Yeah, we are going to go through them to understand the concept. Number 1, what is what exists between two variables when the values of one variable are somehow associated with the values of the other? Correlation, by the way, okay? Not linear correlation, just simply correlation, because it doesn't mention linear. Yeah, it says somehow associated. Yeah, it doesn't matter, it doesn't say specify what type of pattern. So just the correlation. Number 2, yeah, you can stop me if you have any questions, all right, guys? Number 2, when determining whether there is a correlation between two variables, one should use a what to explore the data visually. Visual examination. Yeah, anyone want to contribute idea? Yeah, what should we have here? When determining whether there's a correlation between two variables, we should examine what? What's the name of the type of graph? Yeah, exactly. Scatter plot. Awesome. Perfect. Scatter plot. There we go. Yeah, scatter plot mainly is used to determine the correlation. Number 3, which of the following statements about correlation is true? Okay, here we are looking for the statement that is true. A, we say that there is a positive correlation if the x values increase as the y values decrease. Oh, that's not positive, that's negative, so this is wrong. This is wrong, sorry. B, we say that there is a negative correlation when x increases, if x increases as the y increases. Okay, that's true. Which of the following about correlation is true? We say that there is a negative, oh my god, I'm sorry, negative is not true. So actually, if we change this to negative, change this to positive. They are going to be both true, right? Yeah. So negative relationship means the value of x and the value of y, they go opposite direction. And positive correlation means both x and y go to the same direction. When x goes up, y also goes up. When x goes down, decreases, y also decreases. Part C, we say that there is a positive correlation between x and y if x increases as the y increases. Okay, that one should be the true. D, we say that there is a positive correlation between x and y if there's no distinct pattern in the scatter plot. It doesn't make any sense. If there's no distinct pattern in the scatter plot, we would say there's no correlation, right? We would say there's no correlation. Okay, for the three false statements, we actually corrected them both. Here, use the red color. Any question about this problem? I think it's pretty straightforward, especially if you have a good foundation in algebra and you have taken straight line, the chapter, a linear equation in two variables, and this is pretty straightforward. Number 4, what measures the strength of the linear correlation between x and y? Linear correlation coefficient, right? Yeah, the notation for the linear correlation coefficient is the lowercase letter r. Very, very important. Linear correlation coefficient. Number 5, which of the following not a requirement? Yeah, so here we are going to find the statement which is not a requirement in determining whether there is a linear correlation between the two variables. Let's look at the 4 answer choices. If r bigger than 1, not possible. Okay? R is not possible bigger than 1. Remember, R has to be between -1 and +1. It's not possible for R to bigger than 1. So obviously A is incorrect. Okay? A is incorrect. B, any outliers must be removed if they are known to be errors. Yes, because linear correlation coefficient is very sensitive to any outliers. The value could be very, very different. The value of R would be dramatically different with and without the outlier in place in the sample. So if we know the outlier is error, then we should really remove it. So B is correct. C, a scatter plot should visually show a straight line pattern. Yes, that's the first thing we need to do to determine the linear correlation between two variables, right? Visual examination. D, the sample of paired data is a simple random sample of quantitative data. Yes, that's correct. Yeah, we don't do qualitative, right? There's no possible to do qualitative data. It has to be quantitative numbers. Those are points corresponding to ordered number pairs. And it is required to be simple random sample. For some reason, my stylus is not working. Let's see. Let me restart this to see if I can fix it. Let me see. There's a glitch here. I'll just see it clearly. Number 5, the answer is A. It doesn't let me write. I'm sorry about that. I have no idea what happened. Is okay, guys? Number 5, the answer is A. Do you agree with me? Yes, suddenly the it doesn't let me write. Okay, thank you. Thank you for your understanding. Number 5, A is incorrect. So that's the statement we need to choose. Yeah. Number 5 is A. Again, number 5 is A. And let's go ahead to next question. Number 6. Which of the following is not a property of the linear correlation coefficient? Yeah. Pay attention to the capital letters NOT. We need to choose the statement that does not describe the property of R. A. The value of R is not affected by the choice of X or Y. That is correct. That is correct. R is not affected by the choice of X or Y. Means if you switch X and Y, it means you have two variables, right? If you let the first variable be X, second variable be Y, you get a value of R. Well, what is gonna be the same? The R value would be the same if you let the second variable be X, the first variable be Y. So it really doesn't matter because based on the formulas you can see is symmetric. That's why the hypothesis test is a two-tailed test. Everything is symmetric. So A is correct. B, the value of R measures the strength of a linear relationship. Correct? It doesn't mention correlation, but yes, it is a linear relationship. C, the linear correlation coefficient R is robust. That is, a single outlier will not affect the value of R. No, that's not correct. R is very sensitive to outliers. The existence of an outlier would dramatically change the value of R. Dramatically change the pattern. So C is going to be one we're going to choose. Let's look at the last answer choice, D. The value of R is always between -1 and 1, inclusive. Inclusive means R could equal to 1. R is also could be equal to -1. When R equals 1, that means the linear correlation very, very strong. When X equals -1 means the negative linear correlation very, very strong. So again, guys, this question we choose C. Okay, C as in cat. C as in cat. Number 6, we choose C. Number 6, we choose C. Number 7, which of the following is not one of the 3 common errors involving correlation? Yes, we do have 3 common mistakes when it comes to linear correlation or correlation. Yeah. So the first common mistake is people often mistake correlation as causality. Yeah, let me explain. So if we say there is a linear correlation between two variables x and y, it really does not mean one variable causes the other variable. It's possible, but no, but not sure, not necessary, but not necessary. Because the correlation only measures the linear pattern between the two variables. It does not measure the causality or test the existence of causality at all. Causality is one thing, correlation is another thing. So the first common mistake is people mistake correlation as causality. So answer choice A, correlation does not imply causality is a true statement. Okay, it is a true statement. Yeah, part A, correlation does not imply causality. That statement is correct. Let's look at D, because D also involves causality. D says the conclusion that correlation implies causality. That is a mistake. Okay, that is a common mistake when it comes to correlation. And B, mistaking no linear correlation with no correlation. Yeah, no linear correlation doesn't mean it doesn't have other types of correlation, right? As you can see earlier, when we look at the 4 plots, scatter plots, the one on the right bottom, that one is a quadratic correlation. Yeah, correlation could have a different pattern. Yeah, the one on the bottom right, that's a quadratic correlation. It's not linear, but it is correlation. So second mistake is people mistake no correlation as no linear correlation. Hold on. The people take a no linear correlation as no correlation. Where am I here? Oh, this one. Yeah, people mistake no linear correlation as no correlation. That's a mistake. Part C, the use of data based on averages. That's also a mistake. We should not do that because when we use average values, we smooth the data. If there is a linear correlation exists, if you use averages, the strength of the linear pattern will become very strong, a lot stronger than you use the raw data. I think the best description of that part is right here. We can look at it together. Number 2, using data based on averages is a common mistake. Averages suppress individual variation and may inflate the correlation coefficient. One study produced a 0.4 linear correlation coefficient for a paired data relating income and education among individuals, but the linear correlation coefficient became 0.7 when regional averages were used. Regional averages were used. It's like you use the average, like a mean of this school or this institution, and the average of the income from the other organization. And if you use the organizational average income, if you use the averages, and the linear correlation coefficient would be bigger, would be closer to 1, stronger. Because when you use the average, you smooth the values, make them more closer to each other, and you reduce the variation. Does that understandable, guys, for this common mistake? When you yourself do the research and you want to find the correlation coefficient for the linear pattern, you should use the raw data, like individual data value, instead of averages. Let me know. Okay, yeah, thank you. So number 6, right? Number 7, sorry. Number 7, we should choose A. A is a true, yeah, thank you, Charlie. Number 7, we should choose A. A is a true statement. It is not one of the 3 common mistakes involving correlation. Number 7, we choose A. the first option. Number 8, which of the following is not true for a hypothesis test for correlation? Let's see. A, if the absolute value of R no more than, which is less than or equal to, the critical value, we should fail to reject no and conclude there's not sufficient evidence to support linear correlation. The first part of the sentence is correct, but the second part is not correct. When we fail to reject no, hold on, sorry. When fail to reject no, we fail to support the, there's not sufficient evidence to, okay, that's correct, my bad. A is correct, okay? When absolute value of R is less than or equal to critical value, means the R fall in the blank region, not the two tails. We fail to reject no. When we fail to reject no, remember no is rho equals 0, so we're gonna fail to reject. So we do not have sufficient evidence to support the claim that there is a linear correlation between the two variables. So A is correct. B, when the absolute value of R is bigger than critical value, we should fail. Okay, that one is incorrect. All right, guys, we should choose B. B as in banana. We should choose B. That's incorrect. When absolute value of R is bigger than critical value, we should reject no and support the existence of the linear correlation. C, if p-value is low, means less than or equal to the significance level, we reject no and support the claim of a linear correlation. That's correct. D, if p-value is high, we fail to reject no, and there's no sufficient evidence to support the claim of linear correlation. Okay, so number 8, we choose the answer B. B as in banana, the second answer choice. All right. Number 9. Okay, it's not multiple choice question anymore. We have 54 wild bears were anesthetized. I don't know how to pronounce that, I'm sorry. I probably know how.
Anesthetized.
Anesthetized. Like
Anesthetized.
Anesthetized.
Yeah.
Put in sleep, right?
Yeah.
Okay. So 54 wild bears were put into sleep, and then their weights and chest sizes were measured. That's interesting experiment. So they measure their weights and their chest size and listed in a data set. Results are shown in the accompanying display. Is there sufficient evidence to support the claim that there's a linear correlation between the two variables? Yeah. The first variable is the weight of the bear. The second variable is the chest size of the bear. When measuring a sleeping bear, is it easier to measure the chest size than weight when measuring a bear in sleep? Is it easier to measure chest size than weight? Probably. If so, does it appear that a measured chest size can be used to predict the weight? Or if there's a linear correlation, use a significance level alpha equals 5% to test it. All right. So is to test the claim that there is a correlation, linear correlation between the two variables, right? As you can see, the no is going to be I don't know why that doesn't work suddenly. Let me see if I can use my finger. I can move it. No. Okay, so the no h sub 0 is rho equals 0. The alternative h sub 1 is rho not equal to 0. All right, now how do we find r? R is a given in the table. We really don't have to calculate using any method, but we do have to round it. If we round it to 3 decimal places, and the answer is going to be 0.955. Okay, I can do this. Yeah, 0.955. Critical value. We would have to use the table to find the critical value. All right. Where's the table? Well, we need to remember the sample size. Sample size is 54. Significance value alpha is 5%. Okay, so let's look at the table here. Remember what's the sample size? 54, right? We don't really have 54. But alpha equals 0.05 is going to be the second column. N equals, let me double check what's the, oh, critical R. I'm sorry. Critical R is given. Critical R is given. We don't really have to do nothing. Critical R we have two critical R, okay? Is rounded to 3 decimal places, is positive and negative 0.268. Yeah, we should choose B. Okay, we should choose B here. Yeah, we always have two critical values when it comes to correlation because of the symmetry. And here, is there sufficient evidence to support the claim? Well, let's see. Our R is 0.955. Our critical value is positive 0.268 and negative 2.68. So what's the absolute value of R compared with the critical value? Is it bigger or less than or equal to? Is bigger, yeah. Thank you, Charlie. Yeah, so when the value of R is bigger than the critical value, yeah, in this case, bigger than the positive critical value, that means the R fall in a critical region, and we need to reject no. When we reject no, we support the correlation. When we reject no, we support the correlation. So we choose the second one. Okay? Because the absolute value of a test statistic exceeds the critical value. So we should choose B, the second one. When measuring a bear in sleep, is it easier to measure chest size than weight? I would say yes. If so, does it appear that a measured chest size would be a good prediction for the weight? I would say yes. Yeah, it is easier to measure the chest size than weight. You don't have to move the bear, right? Because measuring the weight would require lifting the bear onto a scale. The chest size could be used to predict weight because there is a linear correlation between the two variables, and the linear correlation is pretty strong, is 0.955. Yeah, it is going to be a good prediction. All right, that's number 9. Number 10. The given table, correlation matrix, have two variables, paper and glass. And let's see, 0.3151 should be the value of R. Yeah, it is. The no would be rho equals to 0. Switch them here. And the alternative would be rho is not equal to 0. Yeah, always like that, right? For the formal hypothesis test of correlation, the no is always rho equals 0. The alternative is always rho not equal to 0. R is given from the matrix is 0.315 if we run to 3 decimal places. For the critical values, it doesn't give us the critical values. We would have to use the table. What is the sample size? A data set includes weights of garbage discarded in 1 week from 62 different households. Okay, sample size is 62. Let's remember that. Alpha is 5%. 62 and 5%. 62, 5%. So 5% is the column in the middle. 62, we have 60, right? And then we can only use the 60. So 0.254. Do you see that? 60. When the sample size n equals 60, pretty close to 62, and alpha equals 5%, the critical values are positive, negative 0.254. 254. Okay, let's remember that. So the answer is A. There are two critical values, R equals plus minus 0.254. The table isn't the most accurate table, so when it doesn't provide the critical values for sample size equal to 62, then we can only use the closest sample size, right? Use the 60. And the last part, because the absolute value of the test statistic is greater than the positive critical value, well, our R is 0.3-ish, is bigger than the critical value 0.254. So we reject the no. We say there's sufficient evidence to support the correlation claim. Any questions so far? Yeah, I really apologize for the inconvenience of the technology. It was working fine and suddenly just stopped working. Number 11, use the given data set to complete part A through part C. Use significance level equals 5%. Okay. All right, so let me show you how do we use calculator, TI-84 calculator to construct the plot, scatter plot of two variables. Okay, suppose the values of the two variables are given. Yeah, we have a sample from variable x, we have a sample from y, and the two samples have the same size. Ready, guys? Let's go to stat, edit. Yeah, I have a lot of history data. I'm going to clear everything. I'm going to use the first list and second list. I'm going to enter the values of x in list 1. I have 10, enter, 8, 13, 9, 11, 14, 6, 4, 12, 7, 5. And second list, I'm going to store the values of y. It's going to be decimal. Yeah, I'll be quiet and focus on entering those values. Please do the same. I will spend a little time to double check my entries. Yeah, for correlation, one very important thing is you have to make sure the order of those values is the same with the order of the values that is given. Okay, if you want to change the value, change the order, you have to change both, change the value for both x and y, because they are matching. You know what I'm saying? They are matching. 10, 9.13, 8, 13, 8.75, 11, 14, 11, 6, 6, 13, 4, 3, 11, 12, 9, 13, 7, 7.26, 5, 4.75. Okay, I make sure my values are correct, and then we go to second y equal, yeah, second y equal. You should be able to see the, it's so tiny for me to see. Let me turn on my light. So please enter second equal. Yeah, on top of y equal, you have, do you see stat plot? Yeah, do you see the key on the upper left corner? It says y equal, but on top of y equal, you have the blue or purplish color says stat plot. Yeah, so you should enter second y equal, and you will see the scatter plots option, right? Yeah. So yeah, let me know, am I clear enough? And then you choose the first one. Yeah, make sure you are turning on the first plot. Okay, awesome. Thank you, Miranda. Yeah, make sure you are turning on the first one. You see ON and OFF, right? Yeah, make sure you confirm plot 1 is on. You know your answer, your graph is gonna be in the first plot. And then you go downward, and you will see the type of the graphs. The first one, the very first one is the scatter plot. You make sure it is highlighted. The background is black. And then your X list is L1. Yeah, for some reason mine is already there. Yeah, X list is L1, Y list is L2. And the mark is depends on your preference. You want a circle, or you want a like cross, or you want the little dot. Yeah, I use the first one because it's big. Yeah, the mark is big. And then now you going to enter. So once you have those settings taken care of, you are going to push the button on the upper right graph. Okay, push the button on the upper right corner. It says graph. In case you don't see the graph, you want to do zoom 9. Okay, yeah, try zoom 9 in case you don't like because of the size of the window, you would probably have to zoom use the zoom 9 to adjust it. Yeah, so zoom 9 is a zoom stat. Yeah, that's a very easy fix for the window. And then you go to the graph again. You should be able to see the whole picture. All right, yeah, and look at your scatter plot and the answer choices A, B, C, D. Which one is the same with yours? B, awesome. You guys great. Thank you so much. Is the second one. Awesome. Very good. Yeah. And part B, find the linear correlation coefficient. Well, I would say the pattern is not linear. But since we're required to find the value for R, we would have to do that, right? Yeah. We need to find the value for R and then determine if there is a sufficient evidence to support the claim of a linear correlation between the two variables. Okay, so how do we find the R? Yeah, so we have L1 and L2 ready. Yeah, please keep them there. And now we are going to go to stat. Sorry, no. Oh no, we are going to go to second vars. Sorry about that. Second vars. Yeah. And we're gonna look at the manual for distribution. Remember, that's where do we find normal CDF, inverse normal, something like that. Yeah, but this time in the manual, we are going to select letter F. Oh, no. I'm sorry. No letter F. What is it? Oh, hold on. My bad. It is stat tests. And not second vars. It's stat tests. Letter F is there. C, D, F. Okay, yeah. So I apologize. Is stats. Yeah, let me type here. Yeah, it is F. Yeah. So once you have L1 and L2, Ready? Go to stat, test, and choose letter F. Yeah, that's the function we need to apply. Yeah, the letter F is linear regression t-test. Is a test. Linear regression t-test. Okay, yeah, so that's the function or the test that we need to apply. So confirm linear regression t-test. Make sure your x list is L1, your y list is L2, same with earlier, right? And keep frequency as 1. And how do we choose the type of the test? There's only the first one always, okay? Row is not equal to 0. It's always a two-tailed test. Yeah, always choose not equal to 0 for this test because it's always a two-tailed test. And then we confirm to calculate. All right, guys. I can only say describe. I cannot write. I apologize again. So you would see y equals a plus bx, something like that, right? Rho is not equal to 0. Tell me what is your t? My t, yeah, t is the test statistic, by the way. T is the test statistic. I have t equals, let me just round it to 4 decimal places. I have 4.25 or 6. Do you have the same thing? Okay, awesome. Same thing, yeah. And what about our p-value? The entry right below it is a p-value, okay? Yeah. If you want to use the p-value test method, my p-value is 0.002127,977. Yeah, awesome. Very good. Perfect. Yeah. And compare with the alpha significance level. Let me double check the significance level here. 5%. Yeah. Significance level is 0.05. So the p-value is very low. P-value is low, no must go. So we should reject the no. All right? Yeah. And what is our R value? Go down. Go down. Tell me what is your R, the linear correlation coefficient. Mine is 0.817 to 6 to 1144. Right? Yeah, exactly same. Yeah, perfect. Yeah, depends on the rounding. Yeah, awesome. Yeah. So from the R, you can see there is a strong linear correlation, and it's positive, right? It is a positive. What are the two variables? Let's see. That's kind of different from what we see from the picture, from the graph, because the graph is not a linear pattern. So X is, it doesn't say what X represents. Doesn't say Y represents either. But from the R value, we would, and also the P value compared with the significance level, we would say we reject no and support the claim of a linear correlation between the two variables. the value of R also indicate there is a pretty strong linear correlation between the two variables. Identify the feature of the data that would be missed if part B was completed without constructing the scatter plot. The scatter plot reveals a distinct pattern that is not a straight line pattern. Identify the feature of the data that would be missed if part B was completed without constructing the scatter plot. Identify the feature of the data would be missed. Yeah, the scatter plot reveals a nonlinear pattern, but the linear correlation coefficient is very strong. I would say is this is 2, 4. Okay, so can you see that the horizontal scale is squeezed? Do you see that? The horizontal scale is squeezed, compressed. So we are looking at a square, right? But the horizontal scale is from 0 to 16, and each unit is 2. But vertically is from 0 to 10, and each unit is 1. You see that? Do you see that, guys? Yes or no? If suppose, actually, if we go to the graph and fix it, if I go to Windows to fix it, if we let the X scale and the Y scale the same thing, yeah, let's go to Windows. If you let X scale to be 1 as well, and the Y scale is also 1, and then we look at the graph. This is 1. Its Y scale is also 1. Delta X, and I look at the graph again, and zoom stat again. Let's try that. It's the same. I would say definitely if we manually stretch the horizontal scale to the normal size, the linear pattern would be better. The quadratic pattern would be reduced. Okay, yeah, because it's supposed to be a linear pattern, by the way. Really should be linear pattern. I don't like this question for that reason. They should have the same unit. They should have the same scale on both x-axis and the y-axis. All right, so let's see what else we have. We have a number 12. It's going to be the same, right? Can you show us number 14 and number 16? Okay. 14 and 16. Let's see. Listed below are numbers of internet users per 100 people and the numbers of scientific award winners per 10 million people. For different countries, construct scatter plots, find the value of the R and find the p-value. determine whether there's a sufficient evidence to support a claim of correlation between two variables. Use significance level 1%. Okay, let's do it together. Let's go to stat, edit. I'm going to clear everything, all right? I like to use L1, L2. So for L1, I'm going to enter internet users 78.2, 78.3, 57.9, and L2, I'm going to enter 5.3, 9.1, 1.7. Oh, suddenly I have a 11. I can see that's an outlier. 11. 0.1. Okay, so now we are going to go to second y equal. Yeah, keep everything the same. Yeah, that's the reason I like to use L1 and L2 because I don't have to do much after that. And then we go to graph. Yeah, mine doesn't show anything, so I'm going to go to zoom, stat, zoom 9, and then I see the pattern. Yeah, do you see the pattern? What is your pattern look like? Which one? A, B, C, D. Mine is similar with the second one. Mine is similar with B. Okay, awesome, perfect. What about R? Where should we go? Stat, tests, letter F. Okay, yeah, we have L1, L2, everything gonna keep the same. If I use L3, L4, at least I have to change L3, L4 a few times. So I always like to use L1, L2. And then calculate. My R equals 0.79. My R, yeah, if we keep three decimal places, it's gonna be 0.795. 0.795, right? And no, always rho equals 0. Alternative, always rho not equal to 0. Test statistic. My test statistic go up. T equals 2.616876878. Round to two decimal places. T equals 2.62. Rounded up to 2.62. Okay. My p-value 0.05899239959. Rounded to three decimal places is 0.059. 0.059. Okay, yeah. Since the p-value is high, fail to reject. Not sufficient evidence to support a claim. Yep, because the R value I have, is not the absolute value of R. Because when you test this, when you test the claim, you have a predetermined alpha. That makes a huge difference. Yeah, since our alpha in this case is 1%. Let me double check. Yeah, 1% is pretty low. That make the p-value high. So it really depends on the situation. So very careful to determine your alpha. So we fail to reject a no. We say there isn't sufficient evidence. Oh yeah, actually similar with the question we just did earlier. And number 16, let's see if it's the same or similar. similar, right? Yeah, they're all similar. I think the rest of the question would be the same. Yeah. The important thing is we know how to use the technology, the calculator, to construct the scatter plot, and then use the function, use the linear regression t-test function to find all the related data, related statistics, t statistic, p-value, r, yeah, something like that. In section 10.2, we're going to continue using that function for the line of the best fit. Yeah. So that's about everything today. It's getting closer to the end of the semester. Did I tell you that I reopened all the assignments? Then you can catch up. Yeah, so if you have some assignments have not gotten 100% yet, then you should work on them and get 100%, because you need it in order to have a better grade, right? If those assignments is completely in your control, you have unlimited attempts. What is challenging is the exams. One attempt that is timed, and you only have one attempt, so that is difficult. So when you have the control over the assignments, try to get them done with 100%. If you have any further questions, please feel free to email me. If you have no question to ask now, I would say have a good night and have a good Thanksgiving, and I'll see you in a week. All right? See you next Tuesday. Bye bye.